Okay, so this is a very surprising line of research for CERN. It has to do with the climate, which is not normally a subject for CERN. In fact, to my mind, I don't know any previous experiment that's been done in climate research at a particle accelerator, a high-energy accelerator, but this is what you're going to hear about. Now, I have to say right at the beginning that it's a scientific talk in scientific language, but I'm going to try as much as I can to make it clear for you. I hope I manage to do that. And don't worry if you don't understand all of it, because even the experts in the field don't understand the climate in any sense of the word perfectly. It's a very complex subject. There's still much we have to learn and understand, and you'll get a little flavor, I hope, in the course of this talk as to some of the uncertainties and some of the complexities of the subject. So let me start. So probably if you're watching the news yesterday, you realize that the Intergovernmental Panel on Climate Change has just released its once every 5 or 6 yearly report on the state of understanding of the climate. And I've lifted a couple of plots from that, so that certainly demonstrates that this is not a stale old talk. This is a brand new talk. And this is one of them. This is showing the, if I can get something out of my pocket. This is showing the global temperature anomaly. This is just the variation in temperature over the last, the industrial period. And what you see is it was fairly constant up to about 1900. Then it went up fairly steeply until about 1945, flattened off for 30 years or so, and then has gone up very steeply since then. And it's this steepness that's coincided with a steep rise in CO2, and the current understanding is that this is being driven largely by CO2. Now, we'll comment a little more on that in the second slide, but there's a little feature at the end here which may have escaped your attention. It may not look like much, but this is a definite flattening. There's no question the temperature of the planet has flattened over the last 13 or 14 years or so. And in simple terms, we don't understand what's causing that. So there's clearly a lot of things that need to be understood. And this is despite the fact that there's been a steady rise in greenhouse gases, and all the climate models that are used to make predictions of future climate would have expected a small temperature rise over the last 10 or 15 years, and we haven't seen that. So scientists are working very hard to try and understand what the origin of that is, because clearly it's going to improve our understanding and improve the precision of climate models when it's properly understood. So at the moment, there are only hypotheses, but nobody can prove or nobody understands it completely. But one of the possibilities is that there's internal variability, namely the Earth doesn't just linearly go up in temperature, but by various means it can absorb energy, or it can, let me explicitly say what I've listed here. One concept is that perhaps the deep ocean is actually taking in a lot of the heat that's arrived on the Earth in the last 15 years or so and buried it in the deep ocean, and so it hasn't appeared as a warming of the surface. That's a hypothesis. But that alone is very interesting, because if that kind of variability internal to the climate system is capable of flattening the global warming, then by the same token, it's also capable perhaps of exaggerating the global warming that's been very important for shaping our understanding of climate change over this period. So it's a big question mark. It has to be understood. Another possibility is that there's something called an unaccounted forcing. Now, forcing is a sort of maybe an unfamiliar word for you, but what scientists have to do in climate is they have to see what the perturbation is, what the change is, that's caused the warming that we see. And so those things are called forcings. And this is by far the most complicated plot you're going to see in this little talk. So don't let your heart sink and don't try and read all the little words. I've put on some things to try and make it a little more apparent to you what's here. But again, this is a plot that only was released yesterday. I didn't see it until yesterday afternoon. Let me try and guide you through it. All these little bars are our current best understanding as to what's causing climate change. So when the bars appear to the right of this line, they're actually warming the planet. When the bars appear on the left of the line, they're actually cooling the planet. And essentially all of these bars, except for this little one down here, are due to human activities. Now, the biggest contribution of all is the famous carbon dioxide. This is the greenhouse gas that you're all familiar with from fossil fuel burning and industrialization and so on. And that's estimated to cause this amount of warming. These units are actually in watts per square meter. That may not be a familiar unit, but a candle is 40 watts. So 2 watts per square meter, and this number here is like having one candle over a 20 square meter area. And it's only that. That's correct. It's only that small amount of heat that's actually causing the net over the whole Earth's surface that's causing the warming that we're observing. Anyway, that's the CO2 contribution. There are contributions from other gases and so on. And so these are all so-called greenhouse gases. Some of them actually cool a little, but net, they're all warming the planet. Now, there's another box here, which you're perhaps much less familiar with, but which is extremely important. And this has to do with so-called aerosols and clouds. Now, you're going to, hopefully, when you walk away from this talk in a few minutes, you're going to understand much more about aerosols and clouds, and you're going to appreciate that they're very important in your life. I'll tell you one simple reason why they're important in your life. If there were no aerosol particles in the sky, there would be no clouds in the sky. So you may not think they're important, but they're very important to you. Anyway, so please sit still and learn a little about them. So at the same time as putting up greenhouse gases, human activity has been increasing aerosols in the atmosphere. And these have two effects. One is that they have a so-called direct effect on sunlight. They absorb or scatter sunlight, and I'm going to show you some pictures because you are very familiar with them, in fact. But they also have a second effect, and that second effect is actually perhaps more important, and that is they form all the seeds for cloud droplets. And all the net effect of those clouds is a cooling effect. Now, there's a very important thing that I haven't mentioned on this plot so far, and that is that these things have little black whiskers on them. These are error bars, which are trying to reflect the level of understanding of each of these contributions. And you see that we think we understand carbon dioxide's warming effect, or at least the initial perturbation on the climate. We think we understand that very well, but we certainly don't understand the effect of aerosols. Anyway, the sum of all these effects gives this red bar. So this red bar represents our understanding as to what changed in the climate system to warm it up. Now, this is more than just academic interest, because the length of this bar divided by the temperature rise that's measured by thermometers, so that's very, very precisely known. That gives a very important quantity called climate sensitivity. It tells you how many degrees the climate will warm up for a certain input of energy. Once you've got that number, that single number, then essentially you know exactly what's going to happen with certain scenarios when you project future climate during the course of this century. So getting this bar right is extremely important. And the uncertainty on this bar, unfortunately, is very big. So the projected future climate for this century is very uncertain. It has a very big range. And it's essentially because this quantity is not poorly known. And in turn, that uncertainty is actually all resting in aerosols and clouds. So that's one of the key take-home messages that I'd like you to try and take away and tell your friends or whatever when they ask you what you did at CERN today. Say that you understand that aerosols and clouds are actually a bigger source of uncertainty than carbon dioxide in what's creating the global warming in the planet. Anyway, so now, there's a second point here, and that is that natural contributions are thought to be extremely small. And that's the solar contribution. It's totally negligible. But one of the questions is, could there be an unaccounted forcing that we haven't included in this plot? We don't know if there is an unaccounted forcing, but this is going to connect us to the cloud experiment because we're going after reducing these error bars here and also understanding if all of the solar contribution is properly accounted for. So two very important aspects. So I said you think you're not familiar with aerosols. You're very familiar with aerosols. Everybody's familiar with the blue haze, and as the blue haze in distant mountains, as it increases, or as the visibility decreases, what you're actually seeing is you're actually seeing those distant mountains through more and more aerosol particles in the atmosphere. These are not cloud droplets, they're just very, very small particles that are obstructing the path, your light path to these distant mountains. And here are some actual photographs with measured concentrations in micrograms per cubic meter of aerosol particles. And in fact, this corresponds to the US air quality standard. I think the WHO recommends 25 micrograms per cubic meter as the maximum level in European cities, but it's this kind of visibility. So that's one effect of aerosols. And here's another picture of aerosols. Early this year, Beijing had some very, very bad. It's quite polluted, the Beijing atmosphere, and it was extremely bad earlier this year. This was an occasion when it had something like 800 micrograms per cubic meter, 10 times more than the recommended, more than 10 times more than the US limit. And this was one view, and here's another view 4 days later. And that's the difference with aerosol particles in the atmosphere. Okay, I mentioned that aerosols form the seeds for all cloud droplets, and that's perhaps their most important climatic effect. And let me try and explain what happens here. And it's shown in this cartoon. If you look out of a plane and see a sort of gray cloud from above, it's because it's actually not very reflective. The sunlight that's falling on it is mostly penetrating. So when you're in a plane up here, you're seeing rather a gray image because most of the light's going through. When you see a nice, really white cloud, it means that there are a lot of raindrops. And there are a lot of, droplets, water droplets. There are a lot of droplets because there are a lot of seeds for the droplets. So the difference between these two clouds, they have identical amount of grams per cubic meter of liquid water, but in this case, when you have more aerosol particles, they're spread over more droplets, and it makes the cloud more reflective and therefore brighter. So increasing the aerosol particles in the cloud makes a brighter cloud, which means it cools the Earth more. And it also makes a longer lived cloud, because this kind of cloud, the droplets are big enough to start falling against each other. And when they start doing that, the cloud sediments out and disappears. So this is a much more longer-lived cloud. Anyway, this process here, which is explained in this cartoon, is, as I say, the largest source of uncertainty in current climate change, the understanding of these aerosol effects on clouds and also the direct effects. Now, where do aerosols come from? Well, there are essentially two categories of source of aerosol, and one of them is where so in scientific terms, what is an aerosol? You're familiar with something to dry your hair or set your hair or whatever. I don't know whether you still use that stuff now. I certainly don't. That is a very particular sort of aerosol. It's a liquid droplet in air. But the aerosol is just this mixed phase, particles suspended in another medium, in this case air. So a particle, an atmospheric aerosol particle, is a solid or liquid particle that's suspended in the air. And typically all air everywhere on the globe has aerosol particles, a few hundred to a few thousand per cubic centimeter, or even more or even less under certain circumstances. Now, these particles are either directly produced, and they're all shown in these cartoons, dust from deserts, volcanoes, sea spray from oceans like the Southern Ocean, biomass burning, industrial production from coal-fired or whatever power plants, and automobiles. Now, there's a second category of aerosols, which is produced from vapors, just gases in the air. So they're not emitted as particles from the ground. They're vapors in the air, and there are only a few vapors that can do this. And they condense and form embryonic particles, which then grow and become big enough for the seeds for cloud droplets. So here we're looking for sources of gases or vapors. And what is known is that sulfur dioxide is very important. In fact, I'm going to click that. A lot of the sulfur dioxide sources are industrial. I mean, we're certainly making a lot from coal-fired power plants. They're coming from automobiles as well, and many other sources. Volcanoes emit a lot of sulfur dioxide. But very importantly, roughly half of the sulfur dioxide is actually coming from phytoplankton on the oceans, which emits something called dimethyl sulfide that becomes sulfur dioxide. Now, it's not the sulfur dioxide that's condensable. That's relatively volatile vapor. When it's in the atmosphere, it gets oxidized by the sunlight, and it makes sulfuric acid. And if you can remember anything from high school chemistry, sulfuric acid is very, very low volatility, and it likes to condense and make particles. Okay, so that's one source, but I put some questions here. Can so-called biogenic vapors also participate in making aerosol? Now, the biosphere, the name that's given to all the vegetation and so on the planet, is actually a very, everybody knows it takes in carbon dioxide and provides oxygen. That's the standard important thing about having the rainforest and so on. We need it to basically give us oxygen that we live on. It also, at the same time, produces a lot of so-called biogenic vapors. These are molecules which, again, you're very familiar with. When you go into a pine forest and smell that lovely smell, you're actually breathing these biogenic vapors. And they're quite heavy, big carbon molecules. They have 10 carbons in them. These are volatile. You wouldn't be able to smell them if they weren't. But the question is, when they go into the atmosphere, they too get oxidized. And can those help form particles? And you notice I've put a question here because we don't know is the answer. We know that they're important. There's a lot of this substance seen in the particles, but we don't know whether it can create them. We know it can grow them. And there's another question here, and that is there's another classes and a particular class of vapors that comes from animal husbandry and also from other sources. And the question is, can these vapors also contribute? So there's a lot of question marks here, but these are the sources. Now, what is gas to particle conversion? It's actually shown in this cartoon here. So what happens is that there are certain molecules in the atmosphere, these very special ones that may be able to condense. They form a little molecular cluster. Literally, it looks something like this. It's a few molecules stuck together. This is one atom, and this is a molecule. This is actually, figuratively, it's a sulfuric acid molecule. It turns out it's extremely difficult to form this first string of particles because these things are colliding all the time in the atmosphere. They collide, stick together for a while, and then break apart. And it turns out very, very difficult to get over a little energy barrier to form what's called a stable particle. But once you form these things, you have what is known, it's an aerosol particle, and it's now stable, and it continues to grow. And if it grows above a certain size, which is very small, only 50 nanometers, it's a tenth the wavelength of light, then it becomes capable of seeding a cloud droplet in the sky. And these will form the seeds for cloud droplets. Now, this cartoon is responsible for half the cloud droplets in the sky. So it's a very, very, very important process. But the second point is, we don't even know the vapors that are condensing here to form these particles. So it's hugely important, but it's extremely poorly understood. And this is one of the key things that we're looking at with the cloud experiment. We're doing experiments in the laboratory. Why do we do them in the laboratory, not the atmosphere? The reason is, when you see them in the atmosphere, the good news is you're seeing exactly what's going on. The bad news is you actually have no idea what caused it, because there's so many sources of variability, and there are so many different processes going on, that you're never quite sure what was the cause that caused the effect that you've just measured. When you do it in the laboratory, you make one change, you see a change in your apparatus. You go back to the old setting, you reproduce the old value. So you have complete confidence, you know exactly what cause and effect is, and you quantify it. Okay, now, I mentioned a second thing, which is that something called solar climate variability, or is there another contribution to the sun, to climate change, that we just don't know yet, or we don't have an established mechanism. And the reason for the interest in this is many what are called paleoclimatic studies. These are past reconstructions of past climate in the pre-industrial age. So there's no question these are natural climate changes. They have nothing to do with human activities, but they exist. We've measured them in these so-called paleoclimatic archives, and in many cases, we have no idea what's causing them. And this is one example of a paleoclimatic reconstruction. In this case, well, there are two curves here. The black curve is actually showing what's called ice-rafted debris in the North Atlantic. When icebergs drift in the North Atlantic, all the pebbles and so on that they've ground off, the glacier ground off the rock, is then melted and rains down, and one can reconstruct from ocean sediments what the past record of glaciers were past the spot where you're looking and doing your drill core. And that varies with time. We're here today. This is going back 10,000 years. And when this thing is low, this black line, there are a lot of icebergs in the North Atlantic. And when it's high, there are very few. So this is warm climate, cold climate. The second curve is a red curve that shows something called cosmic rays. And this is something that I'm a particle physicist, but I'm sort of very much part of the cloud experiment. That's something that CERN does. So here's the link. This is why CERN got interested in climate change, because cosmic rays are definitely CERN's business. It's actually in the CERN constitution. So we're legally obliged to look at cosmic rays. Anyway, it turns out, what are cosmic rays? They're high-energy particles, just like the particles that are made by CERN accelerators. They're produced in supernovae somewhere in the Milky Way. They take a few million years. They may arrive on the Earth's climate, and they shower high in the atmosphere, and produce a shower of particles. What they do in the process of that is they create a weak ionization in the atmosphere. There are about 1,000 ion pairs. That means atoms with either a plus charge or a minus charge floating around in the atmosphere. And there's about 10 cosmic rays per second going through all of you. They actually have probably been very important for all of our mutations and development to arrive where we are. But that's a long, very interesting subject, which I can't discuss. Okay, so they're responsible for a weak ionization in the atmosphere, and the question is, could this ionization affect the formation of aerosol particles? And I should say that the variation of cosmic rays, which is shown by the red line here, and I've omitted a very, very important point. The cosmic rays also vary. They vary because of, in this case, changes of the solar wind. The strength, the magnetic intensity of the sun is modulating the quantity of cosmic rays that reach the Earth by 10 or 20%. And it's quite remarkable, but it seems that these two curves are correlated. Mathematically, it's well beyond a random coincidence. There's some connection between those two, but they seem to be totally separate processes. But the hypothesis is, could these ions influence aerosols and thereby clouds? And we don't know the answer. It's absolutely not established. There's very contradictory evidence one way or the other way. And again, we're going after this with the CERN cloud experiment. So now I've got to show you in the last few slides what the CERN cloud experiment is, and then we'll finish. So this is the CERN cloud experiment, and here's a typical physicist for scale. It's actually typical physicist by gender. It's quite remarkable, but we have almost parity, or more than parity, I'd say, in terms of our I think the politically correct word is gender mix on the experiment. Anyway, so there's a typical cloud physicist for scale. It's a 3-meter chamber. It's a very clean stainless steel chamber. We believe it's the cleanest chamber in the world under these conditions. It's about 1,000 times cleaner than previous experiments, and because of that, we're finding unique results, which we're publishing now. It's instrumented to measure the temperature. It's filled with certain gases that are very carefully controlled. There's a huge attention to detail of the construction and the materials used in the chamber. We don't use plastics anywhere. We're following ultra-high vacuum practices from CERN. I mean, CERN is full of accelerators and detectors, but it also has, under one roof, some of the best technical and engineering people anywhere, in any institute in the world. And we put essentially all the CERN know-how that we can into designing and building this thing. So that's the chamber with the gases and so on. What we do to do experiments is we attach state-of-the-art instruments which continually extract small amounts of the gas and measure what's going on in the chamber. And we surround the whole thing by a thermal housing and maintain the temperature very stably to a order 1/100th of a degree anywhere corresponding to anywhere in the troposphere from, say, minus 70 degrees up to plus 30 or 40. And the style of the experiments is we essentially establish a parcel of air in the chamber in a chosen region of the atmosphere with a certain number of vapors, and we then cook it and follow it over a number of hours and watch the production of these particles. And then we change one parameter and do the experiment again. So this is what it looks like. It's across the road somewhere. I'm afraid you can't see it because there's a huge amount of concrete construction going on, and it was deemed unsafe, I'm afraid, for people to visit it. But this is the chamber. It's actually the thermal housing. A couple of years ago, these are equipment that's connected to sampling probes which go into the chamber, and this is a view of it about a year ago. And on the top, we've actually added now the capability to do what are called adiabatic pressure expansions. So not only can we grow these aerosol particles, but we can also create liquid clouds in the chamber. So this is an example of gas to particle conversion seen in the atmosphere. This is what it looks like in cloud. Time is running along here in both cases, and the red band, oh, and this is size of particle. This is 10 nanometers, 100. This red band corresponds to a lot of new particles. Blue means practically nothing, red means a lot. So what you see here, suddenly just after midday, and this was in Finland, a lot of new particles growing up from molecular sizes. And when they reach this size, they're capable of seeding cloud droplets. So that's the atmosphere, and this is the equivalent thing that we're doing in cloud. It's exactly the same process, except we know exactly what the conditions are. And you see these bands, or we call these banana plots, changing, and we know exactly what change caused each of these. This actually is a very interesting plot because we only made ion changes of the CERN beam and so on during the course of this, so you can see there's a clear effect. Okay, so I'm going to show you a couple of plots now, just before finishing. And I'm afraid these are scientific plots. But let me try and step you through these. First of all, they're log scale. So this is 10 times more than the previous one, and that's 10 times less. So 1 tick is a factor of 10. This is measuring the concentration of sulfuric acid. And this point here, just to tell you how difficult these experiments are, that corresponds to a concentration of sulfuric acid vapor of 1 molecule per trillion air molecules. So this is the limit of contamination that you can get in this chamber. But we can control the sulfuric acid at this level and have no contaminant. We have contaminants, but not important ones, at the level of parts per trillion in the chamber. On this scale, we're measuring the production rate of these new particles. So the way you look at this, for example, if you put 10 to the 7 particles per cubic centimeter of sulfuric acid, these are the atmospheric data, by the way, then you'll get about 10 particles created in the atmosphere per cubic centimeter per second. These are the observations. Now, the very first measurements we did, which were published a couple of years ago in Nature, we just put sulfuric acid in the chamber. And we measured that this was the production rate of particles at different concentrations. So you can see that this line is way, way below that. So for example, at 10 to the 8th sulfuric acid, we're 4 or 5 orders of magnitude below the atmospheric value. So the first conclusion is that does not explain atmospheric nucleation. Now, you may say, well, that's a negative result. Why is that interesting? It's very interesting because before this result came out, everybody expected that this vapor plus the next one, and I'll show you the next one, ammonia, explained all of these points. So the first result from cloud essentially took a giant step backwards for mankind, or at least for climate science, and said we actually know less now after the cloud result than we did before we started cloud. So perhaps we shouldn't have done the experiment. You know, ignorance is maybe more comfortable than reality. But anyway, that was the result. So we're in a position here where we don't know what the vapors are. So we've been doing since then, that was 2 years ago, we've been studying other vapors, and I can't show you what the answer is. In about a week, actually, in Nature, we're going to publish a paper which does actually have data that gets into the atmospheric region, but I can't talk about it. I'd love to talk about it, and scientists hate not to be able to talk about their stuff. So this hurts me more than it hurts you, all right? But anyway, if you read Nature, or I don't know, read a CERN press release or something, you'll see that we've got some explanations for what can cause this stuff now. Now, why is that important? Is it just sort of academic interest? You know, scientists are legendary for just liking going off in a corner. They don't care if nobody else likes it. They like it, and that's sufficient justification, providing they're getting paid, you know, and they get their money for their equipment. And that's certainly true of me, like most scientists. But anyway, this happened to be important, okay? So I'll just finish by saying why it's important. What these first cloud results, and the fact that those lines did not go through the atmospheric observations, what this implies is that there must be another vapor together with sulfuric acid. We believe, all our understanding is that sulfuric acid has to be involved, but it's not sufficient. There's another vapor, as yet unknown, which is forming half the seeds for the cloud droplets in the sky, forming seeds for half the cloud droplets in the sky. It's got to be organic because those are the only vapors left. And it's very important to identify these vapors. Why? These are possible sources. They can be livestock, industrial, or autos, or these so-called biogenic vapors. And they, as I say, get converted by sunlight in the atmosphere. If it's anthropogenic, livestock, autos, and so on, then there could be a new climate forcing from human activities. If you try and remember that very first plot at the beginning, it showed that these aerosol particles have a big effect on the climate through direct effects and through effects on the clouds. And if there's another contribution, then those little bars that you saw in the IPCC plot need to be modified. There's got to be something more that's going on. So there could be a new climate forcing which will change the equation as to what is the total forcing, and that will change the projections for how much we will or won't warm the planet, how much we will warm the planet during the course of this century. On the other hand, if this other vapor is mainly biogenic, then we have the possibility of a new, very important climate feedback, namely, when trees are stressed, they emit more vapors. And if those vapors are capable of making more particles in the atmosphere, this is actually something that is known to some people as this Gaia hypothesis, that the biosphere can help control the climate and make it more conducive to its own existence. So we don't know. It's very important to put these question marks in. These are possibilities. We don't know them, but that's why it's important. Okay, so what's the summary? What's the take-home message? So the take-home message that you should try and remember is that aerosols and clouds are very important and form the largest uncertainty in anthropogenic climate change. And the second take-home message is that there's evidence in paleoclimate reconstructions that there's something called solar climate variability, and there is no established mechanism for that. And in the past, those climate changes are comparable to the climate changes we're experiencing today. I don't want to get into any discussion about are they a little bit bigger, are they a little bit smaller. We actually don't know well enough, but they're not small, they're comparable, okay? So we really have to understand this. It's also important to point out that the sensitivity of the climate could be different in the pre-industrial age. We have many more aerosol in the climate now, and even though it was sensitive in the past to these changes, perhaps it's not sensitive now. I'm not saying that's the case. I'm simply saying you cannot make a simple conclusion. It's a very, very complex subject, but it's